The James Webb Space Telescope has detected a combination of gases in the atmosphere of the exoplanet K2-18b that could represent one of the strongest hints yet of possible biological activity beyond Earth. The planet, located more than 120 light-years away in the constellation Leo, appears to contain methane and carbon dioxide along with a possible trace of dimethyl sulfide, a molecule that on Earth is produced primarily by marine microorganisms. If future observations verify the molecule in the planet's atmosphere, it could become one of the most compelling potential biosignatures ever detected on a world beyond our solar system. The planet at the center of this discovery lies about 120 light-years away in the constellation Leo, known as K2-18b. It is very different from Earth in many ways, yet it occupies a region around its star where conditions could allow liquid water to exist. Astronomers call this region the habitable zone, a band of space where temperatures are neither too hot nor too cold for water to remain liquid on a planetary surface or beneath its atmosphere. The star that K2-18b orbits is a small, cool red dwarf, far dimmer than our Sun. Because it emits less energy, the habitable zone lies much closer to the star than it does in our solar system. K2-18b circles this star roughly every 33 days, placing it comfortably within that potentially life-friendly region. Despite its promising location, K2-18b is not an Earth twin. It is significantly larger, with a mass about 8 to 9 times that of our planet and a radius roughly 2.5 times greater. Planets in this size range are often referred to as sub-Neptunes, meaning they fall somewhere between Earth-like rocky worlds and the larger gas giants like Neptune or Uranus. For years, astronomers struggled to understand what such planets are actually like. Some may be miniature versions of gas giants, wrapped in thick atmospheres with no solid surface beneath them. Others could be entirely different types of worlds, unlike anything found in our own solar system. One intriguing possibility is that K2-18b belongs to a class of planets that scientists call Hycean worlds. The term combines the words hydrogen and ocean and refers to planets that may possess vast global oceans beneath hydrogen-rich atmospheres. In these environments, the atmosphere could act like a blanket, trapping heat and maintaining temperatures that allow liquid water to exist below. Even if the planet itself is larger than Earth, the presence of a deep ocean could create environments where simple forms of life might potentially survive. If such planets are common in the galaxy, they could greatly expand the number of places where life might emerge. Determining what the atmosphere of a distant planet is made of is not easy. K2-18b is far too distant for any telescope to directly photograph its surface or oceans. Instead, astronomers rely on a clever technique known as transmission spectroscopy. Each time the planet passes in front of its star from our point of view, a moment called a transit, a tiny fraction of the star's light filters through the outer layers of the planet's atmosphere before reaching Earth. As that light travels through the atmosphere, certain wavelengths are absorbed by the gases present there. By carefully measuring which wavelengths disappear from the spectrum of the starlight, scientists can identify the chemical fingerprints of the molecules responsible. This is where the power of the James Webb Space Telescope becomes crucial. Launched to study the distant universe with unprecedented sensitivity, the observatory is equipped with instruments capable of detecting extremely subtle variations in infrared light. These instruments allow researchers to examine the atmospheres of exoplanets in far greater detail than was previously possible. When astronomers directed Webb toward K2-18b during several transits, the telescope recorded a spectrum that revealed the presence of several important molecules. Among the gases identified were methane and carbon dioxide, both of which contain carbon atoms and play important roles in planetary atmospheres. The detection of these molecules was significant because it confirmed that carbon-bearing chemistry exists in the atmosphere of a planet located within the habitable zone of its star. On Earth, carbon-based chemistry is the foundation of life itself, although the presence of carbon alone does not necessarily mean that life is present. Many non-biological processes can produce methane and carbon dioxide, and both gases are found on planets and moons throughout the solar system. What truly captured the attention of researchers, however, was the possible hint of another molecule, dimethyl sulfide, often abbreviated as DMS. On Earth, this compound is produced primarily by living organisms in the ocean, especially microscopic plankton that drift near the surface. These tiny organisms release DMS as part of their metabolic processes, and the gas eventually escapes into the atmosphere. In fact, the vast majority of dimethyl sulfide found in Earth's atmosphere originates from biological activity in the oceans. Because of this connection, scientists consider DMS a potential biosignature gas, a molecule whose presence might suggest that life is active in the environment where it is detected. The possibility that such a molecule might exist in the atmosphere of K2-18b immediately sparked intense interest. If the signal is genuine and cannot be explained by non-biological processes, it could hint that living organisms might exist somewhere on or within that distant world. Yet astronomers are the first to emphasize that this is far from proof of alien life. The signal detected by the James Webb Space Telescope is still relatively weak, and interpreting spectra from distant planets is an extremely complex task. Many different molecules can produce similar patterns in the data, and researchers must carefully test a wide range of possible explanations before identifying the most likely one. Even small uncertainties in the data can sometimes lead to misleading results. The statistical confidence of the DMS detection also remains below the threshold typically required for a confirmed discovery in astronomy. Scientists often look for a level of certainty known as 5 sigma, which corresponds to a probability of about 99.94% that the result is real and not due to random fluctuations. The current signal associated with dimethyl sulfide is closer to the 3 sigma level, which means there is still a meaningful chance that the signal could disappear with further observations. There are also other possibilities that must be considered. Planetary atmospheres can host complex chemical reactions driven by sunlight, heat, and interactions between different gases. In environments very different from Earth, it is possible that unfamiliar processes could produce molecules that resemble biosignatures without involving life at all. Some scientists have suggested that other sulfur-containing compounds might mimic the spectral signal attributed to dimethyl sulfide. Until more data are collected, distinguishing between these possibilities remains difficult. Despite these uncertainties, the discovery has already had a profound impact on the search for life beyond Earth. Only a few decades ago, scientists had no direct way to analyze the atmospheres of planets orbiting other stars. The first confirmed detection of an exoplanet around a Sun-like star occurred in 1995, and at the time the idea of identifying atmospheric molecules on distant worlds seemed almost impossible. Today, with telescopes like the James Webb Space Telescope, researchers are not only detecting those molecules, but beginning to discuss whether some of them might indicate biological activity. Future observations will play a crucial role in determining what is really happening on K2-18b. Astronomers plan to continue studying the planet during additional transits, collecting more detailed spectra that could confirm or refute the presence of dimethyl sulfide. The more times the planet is observed, the clearer the picture of its atmosphere will become. If the DMS signal grows stronger with additional data, confidence in the detection will increase. If it fades away, scientists will know that the original signal was likely caused by noise or a different molecule. Researchers will also search for other potential biosignature gases that might appear alongside dimethyl sulfide. On Earth, biological activity often produces a combination of gases rather than a single chemical marker. Finding multiple molecules that together point toward biological processes would make the case for life far more compelling. At the same time, scientists will refine computer models of planetary atmospheres to explore whether purely chemical processes could generate similar signals without the involvement of living organisms. The broader significance of this discovery extends far beyond a single planet. K2-18b may represent just one example of a type of world that could be common throughout the galaxy. Sub-Neptune-sized planets appear to be among the most abundant types of planets discovered by astronomers so far. If many of them possess hydrogen-rich atmospheres and deep global oceans, the number of potentially habitable environments in the universe could be far larger than previously imagined. Instead of focusing solely on Earth-like planets, scientists may find that life could emerge under a much wider range of conditions. This shift in perspective reflects a growing understanding that the universe may be far more diverse than the solar system alone suggests. For much of human history, our planetary neighborhood provided the only examples available for study. The discovery of thousands of exoplanets over the past 3 decades has revealed an astonishing variety of worlds, scorching hot planets orbiting extremely close to their stars. massive gas giants drifting in wide orbits, and strange intermediate planets unlike anything seen in our own system. Each new discovery adds another piece to the puzzle of how planets form and what conditions might allow life to arise. Even if K2-8 ultimately turns out to be lifeless, the observations made by the James Webb Space Telescope demonstrate that astronomers now possess the tools needed to investigate the atmospheres of distant planets in extraordinary detail. Future telescopes, both in space and on the ground, will build on this capability. Instruments currently under development are designed specifically to search for biosignatures on Earth-like planets orbiting nearby stars. As these technologies improve, the search for life beyond Earth will become increasingly precise and comprehensive.